Okay, good afternoon. Nice to meet you again. And this is chapter 4, another step in water treatment plant, which is about water treatment plant filtration and disinfection. Let me just give you a review of what we had in the previous one. Yeah, the day restoration. Okay. As a review, we say that in the previous chapter that we have, after the process of sedimentation, this was the sedimentation. There is another two process that's coming after this one, which is what? Which is the process of adding some chemicals like most commonly used was alum. So we will add some alum to this tank, and we will do rapid mixing or rapid mixing, and this tank is called rapid mixer. Rapid mixer tank, and the rapid mixer tanks, why it's rapid? Because we have a value of G. Do you remember the value of G? Have you ever?
500 to 1000 per second.
Yeah, it's 500 to 1000 per second. It will be in per second or hertz. Then that means we will have this one, and the rate of the flow, the Q and the R, they are related to each other by having the G. This G will be equal to P and the volume of the tank and the viscosity. So we have a range for that one. We have a time. The time consumed or time period for the retention of water in this tank, it will be in terms of minutes. Now, 1 minute to 2 minutes, that will be enough for just mixing the prepared alum and then mix it with the Q. After that, there will be another tank which is called a slow mixing tank. This slow mixing tanks, we have also mixer here, but the mixers here are different than the one that we have here. Usually, will be impeller. Will be wheel rotator. Now, wheel paddle, it will be like this. There will be a wheel paddles, and what is going on here? It is we have a mixed with the raw water, the alum with the raw water that have been mixed here. They will interact to each other. They will interact with the solids that's suspended in the material. Why we are doing all these processes? Because we said in the sedimentation there are somehow some particles, they are less in, they haven't enough size, a way to settle down, so we have to enhance them. So we will add some chemicals in the flash mixers and slow mixing that they will combine between each other, and they will make a flood, and then this is called flocculator tank. This is called coagulation process. Now, then there will be a settling here, and that's now the clean water or the clean one, and usually this is put it in another tank. The clean water here, the water here should be about 90% clean from any settled soil or suspended soil. Now, we wanna, the next step for this one is called filtration. Filtration is the process of, we have filter media, and I think you know about the filter media. What is the filter media? It's called granular filter media. Granular filter media is basically, it's a layer of sand and gravel, but it's not an ordinary gravel. It will be a specific sand, a specific gravel that we have, and we let the flow to pass through this media, and we will have the clean water. 99% of the water will be clean due to this process. So the flow through porous media, the flow through the sand and the gravel are called filtration. Filtration, it is very important for us to have a filtration. If you just have a look on the slides, you can see what kind of here the typical. So basically, we can classify the filters based on their rate. The rate, it means that how much that 1 meter square of this filter. When I say 1 meter square, I mean the surface area of that filter. If it was, we have 1 meter square of this filter, how much it will be capable for treating water. There is a limit for treating water. This is called filtration rate. Filtration rate, that's our sum over FOR. It is the same as SOR. You remember that in sedimentation type we have the surface overflow rate. In filtration we have a term, it's called filtration rate. What is the filtration rate? The filtration rate, it will consider the flow. The Q divided by area. This is called filtration rate. Which area? Area of the filter. Now, if I have, for example, this is the tank that I want to use for filtration. So if was a tank and I will have the Q, I have to put a gravel on this tank, a layer of gravel and a layer of the sand. So the area of this area, this is called area, filter area. This filter area, when I divide the Q by the filter area, it will give me an indication. It's giving me a filtration rate, which is the velocity. Actually, it's the velocity of water just above the filter. Just above the filter, you may have in soil mechanics that we have the V here and Vs here. When we have V in the settling velocity or seepage velocity, it looks like seepage velocity if you have a water above the sand. And so the just above the sand, the V is the velocity, which is the Q over A. But here is the seepage velocity that we have. In filtration, it's exactly the same, but we don't have seepage. It's called filtration velocity. Now, back to what we mentioned here, we have two types of filters based on their filtration rate. Again, where is the filtration rate? The filtration rate is the Q divided by area. Now, what that means, for example, if the filtration rate was 4 meter cube per day, per meter square per day, means each meter square of this filter bed is called, will be capable for treating 4 meter cube per day as a cube. So this is considered if the filtration rate was less than 10 or 8 meter cube per meter square per day. That filter, when the filtration rate is less than this one, it's considered as a slow filtration rate. If they was greater than 10, or it usually will be between more than 60, is called high filtration rate. And this is one of the filtration rate of filter classifications. Again, there is another classification of the filters based on their bed, on filter bed. The filter bed, I mean the materials that will be used as a filter media. Usually there will be a monofilter. So monofilters means one layer filter One layer filters means that only we have only one sand layer or gravel layer or just one layer. That's called monolayer. And we have dual media layer. Dual media layer, sometimes it will be sand or sand plus gravel or sand plus anthracite. The anthracite, terms anthracite, it looks like artificial sand. It's called artificial sand. It will be used for treating water. Now, we can also classify the filters based on their materials. So there is two classifications for the filters based on their performance, whether they have a high filtration rate or whether they have low filtration rate, or based on their filter media, how much the layer of the water, of the sand, of the filter media will be there. Is there's one layer or there's multi-layer? Now, before that, I would like just to show you this one to you. You can see here's the idea of the filtration, right? This is the charcoal or the coal that will be used in as a filter. This is, it means the water is coming in this way and it will be passed here until it will get this one. And then this one is called vitrified vitrified clay. This is let me say this is a pipe which is porous. Inside this pipe there is a hole, no nozzles that will let the water, the clean water, go this way, and it will be cleaned in these pipes. Now, this is exactly they are coming and bringing out the sample of the filter just for information. Now you can see we have cool. Why do we use cool? For the taste. Sometimes we have it's called let me say cool for odor removal. We are using filter also for remove the odor of the water, and this is usually it will be cool or it will be activated carbon. Activated carbon are used for just removing the odor of, and you may have in your fridge in the house some kind of charcoal or activated carbon. Usually it will be used just to remove the odor. Also, we have graded sand. So graded sand means that we have small particles and high, greater in size particles there. After that, there will be gravel, and the gravel will be distributed like this way. Why we are putting the greater size here? Because we want to make the water should be here to prevent the small sand layers to get out from the noses. And there is a way to just keep this kind of gradient stay in the same way. This is when we are going to wash this filter, we just inverse the flow back. When you are inversing the flow back, so what will be firstly moved, the easiest one or the lowest in weight is. So this is will move first, and this is will move second, and so on. The last layer will move is here, this one. And when I'm stopping back washing, so the heaviest one will stay the first one, which is the gravel. It will get back to its original position and so on. So the sequence of the layers stay in the same way. So that's why we need to put these material in this one, and this is called multi-filter layer. Now, I missed to tell you that we are using filter to just remove the color and the odor and the microorganisms and the taste and the iron and the manganese besides. So 99.9% after filtration, the water should stay clean. Now, based on what we say that we have slow filter rate and rapid sand filter, the slow sand filter or slow sand filter is one of the types of the slow rate filters, and rapid sand filter are one of the filters that having a rapid sand filter. Usually, or most commonly, we are using these two types of filters, and we have to know what is the difference between them. When I say this is in common, whether we have a rapid sand filter, and by the way, the rapid sand filter is most nowadays are used very instead, and slow sand filter now it have been gone. So during the 40s and 20s to 40s of the previous century, they were just using the slow sand filter, but nowadays are all working on the rapid sand filter because it's most we need to have a very high flow rate or high clean water in a very close time. Now, here's the distribution of the depth of the filter layers. First of all, we have the under drain. The under drain, I mean by the under drain, here is the under drain. Under drain. This is the under drain. Under drain means that after filtration, there will be a pipe, and this pipe will collect the clean water. There will be gravel. This is the gravel. The depth of the gravel, it will be about 40 to 60 centimeters. After that, there will be sand. The sand, it will be between 60 to 120. So in general, there will be 1 meter depth, 1 meter to 1 meter and 80, 1 to 80. You can say 1 to 180, and this is just gravel and sand. So when you are going to design a filter, you have to just let the water the 2 meters depth just for having a filter media. After that, we will have about 1 meter, another 1 meter, 60 to 90 centimeters more than 1 meter. There will be only 1 meter space for having water in this above the sand. That will become 3 meters. So about 3 meters, maximum 3 meters needed just to have a filter tank. Above that, there will be it's called trough. The trough is it will be here. It will be a channel. This is a channel. Why we have a channel? Because this channel is used to collect when we are going to backwash the filter. The water is coming this way, and it will raise up, raise up, raise up, till there will be. And by the way, I'm stopping Q. This is the Q in, and this is the Q out. When you wanna wash this filter, you have to close the Q in, and you will reverse the Q, and there will be another exit area, which is this trough. So this trough is used just for removing the filtration and the mud. Usually there will be mud and other things will be collected in this filter. Those things are be collected here in this channel and will be disposed out. Can see, yeah, this is the top view, of the channel. This is the filter itself, and the gravel and the sand will be put it here. And after having this area, the waters when you want to wash the filter, the water is coming up this way from the inside. It will get inside, and it will be collected in these troughs. These are channels, and then after that it will be collected here, and it will be drained out. Why we need to drain out this filter? This is the mud and everything, every debris that's collected in the have been filtered out. These are, and we need to from 24 to 48 hours to stop the filters and washing those filters. That's called, this process called backwashing of the filter. So backwashing is just when we need to just clean out the filter. Back to what we have. So the gravel layer, it will be between 40 to 60. When we have a sand layer, it will be 60 to 120. And then we need to have a water about 1 meters. Then there will be a trough, and this trough, as I told you, this is channels will just collect, used to collect, or the backwashed water. And last thing, the gullet. The gullet is the here's this gullet. This is the gullet. Are the use all the troughs will dispose their waste into this gullet. Do you have any question right now? Till now?
No, doctor, thank you.
Okay, so you understood how this is process working?
Yes, sir.
So the process is just, let me simplify to you. We have water, we will pass the water through a bed. Then this is called filtration. I need to clean this filter bed. What should I do? I have to stop the inlet to this one, and I will reverse the water through the bed, and then the whole materials that have been filtered between the filter media, they will be get out from this filter, and we have to wait. Then those materials stay, they will recede in their places again, and then after that the process of filtration will start again. This is a brief description of this filtration. Is it clear?
Yes, doctor.
Okay, and now, okay. I want to tell you that in case that this is, let me say, this is, we have the gravel, and this is the sand, the gravel, and this is will be the water, let me say that the water will be collected here. The free space, we said this is about 40 to 60 centimeters, and there will be it's about 600 to, I think, yeah,
600, 200,
800,
1200.
yeah, 60 to 80 centimeters. Now we have also
No, to 120, sir. 60 to 120.
yeah, 120, 1 meter 20, or from 60 centimeters to 120. Now this is will be sand, right? This is will be gravel. Now, as first thing that we need to know, we have two things when we are going to design this tank, this filter. First of all, when we have a like sedimentation tank, where we should have more than one filter. For example, if this is a filter, we should have another filter here. Why we need at least two? Because one working, and this is standby. You need to have a standby, and you need to have washing. So if the filter is working, then this is standby stop. This is will be used for backwashing. Now we have three filters units, and I can have only the flow from one filter. Why? Because one is standby of that one, and one is used for backwashing. Usually, the number of the filters should be even number, and in all together, those are called filter bank. Okay, that's one. So the number of the filter should be have numbers that like this, and I will give you an equation just to roughly empirical equations. There is an empirical equation to get to give you the number of the filters that is required. And this equation is coming from the experiences. Here is the number of the filters. Yeah. The number of the filters usually will be equal to 0.25 times the Q that we have, total Q power 1/2. Now, for example, if I have 12,000 meter cube per day. Now, taking the square root of that 12,000, how much it will be? It will be 109 times 0.25. So
27.4.
27.3. And we are using 30. Means you need at least 30 filters units. Now, and by the way, why the 12,000 meter cube per day? It should be per day. Okay, empirical. This is an empirical equation. Now, it says that in case that if you get the number of the filters less than within this equation was less than 5, you can just add one other filter. So 5 plus 1, it will become 6. If you get 5 or less, you have to add only one filter. This is just for washing. If the number of the filters, like our case that was between 5 to 30, in our case it was 27, so what should I do? I should add another 2 filters. Now they will become 27.3 plus 2, it will become 29.3, which is equal about 30. Then you just add 2. If the number of the filters were more than 30, so you just add another 4 filterings. This is according to the filtration tax. The number is the number of the filtration tax. This is an empirical equation. We use it for the design of the filter unit. Now, again, this is as a number of the filter. You may have a question about what the materials should be used. I will say that we have a specific sand and specific gravel. What the sand should be used? The sand we have a properties for this sand. It should be clean from the debris. It should be very clean, and we have a specific sand that's called quartz. Quartz is a type of the sand that we have. I mean by the quartz, the sand that's used for manufacturing for glass, making glass and windows. So this is a specific type. I mean, we have it in Iraq, we have it in Romadi. All the sand should we have here. There is a specific. It's filled with the quartz, and it will not be affected by organic matter. How do you know? You have to bring a sample of the sand and pour H2HCl, concentrated HCl for 24 hours and see whether we have any losses in its weight or not. If there was any losses in the weight, it means this sand is not clean. It has organic content in it. Now, this sand will not be allowed to be used in the one. Usually the quartz one is not free from the organic material, should be used here, and the same will be used for gravel. The main point that we have to use the gravel is the gravel should be having a granular shape to should be have a uniformity coefficient. Uniformity coefficient is as you have it, I think, in soil mechanic UC or CEU, it's D60 over D10. It means that when you are going to draw the sieve analysis, there will be from 0 to 100, there will be the diameters of the gravel, and there will be the percentage of percentage of passing or finer than the stated size. So this is the diameter. Usually when you are doing the sieve analysis, you will get the curve like this. For 60% of this passing, you will get the diameter that's giving you this one. It's called D16. And D10 is the diameter that's giving you 10% passing. So dividing D60 by D10, it will give you a number which is called uniformity coefficient. And we have for this gravel that's used in filter, it should be between 1.2 to 1.6. And I think we have it here in the filter media. Yeah. I think we have it here. Where is it? Yeah, this is the uniformity coefficient will be between 1.6 to 1.8. 1.6 to 1.8, it means that this is the shape. It should be S shape. S shape, or it's well graded. It should be well graded gravel. This is one of the most important points that we have to have it. For the sand, we say that we have to have specific, this is for the sand, and D10. D10 usually, as you have it in soil, it's called effective size. Effective size of the sand should be between 0.3 to 0.6 millimeters. And what is that effective size? It's the percentage of the 10% of the sand that will be passing through. This is the most important two ones. Why we have to know that? Because the size, when I say the effective size, it will be 0.3 millimeter. We have an empirical equation. It's called V backwash. V backwashing, the velocity that just needed to just clean this filter, it will be equal to 0.3 meter per minute, the same effective size. So V back is equal to effective size. This is also empirical equation. This will be millimeter. This will be millimeter per minute. So having this kind of soil, it should help us. That's called the effective size, and the V backwashing is the velocity that just needed to just wash the filter. We say this is Q. This is the filtration. Q filter rate. This is Q back or back filtration. The Q back filtration is the reverse of the flow. When it will happen, we need just to use it for cleaning the water. This Q divided by the area of the filter bed, it will give you V backwashing. The V backwashing is the Q backwashing divided by area of the filter. While dividing the Q by the Q filtration by area of the filter will give you filtration rate. So the filtration rate is the Q divided by the area, and the Q back wash or backwash filtration Q is the Q back divided by the area in an opposite way. So this V backwashing, it should be equal to effective size. Also, this is an empirical equation, and we have it for this. The most important things that I want you to see, here's the difference between the rapid sand filter and the slow sand filter. Again, I want to remind you that rapid means a very high rate, slow it means slow rate. They used in, this is the why it's high rate, because every 1 meter square of this filter will can capable for filtering 120 to 200 meter cube per day, while for the slow sand filter we have just for 5 to 8 meter cube per day will be used. So it means that this is will be used for a very little or not high density pollution area. The area, filter area here is usually it will be no more than 40 to 60 meters square. While we need a large area, the space that is needed for this slow sand filter, it will be between 1,000 to 2,000. Then the length to the width, L to W, it will be like this. Usually it will be like a square shape, and the number of the filters that we need here, it will be number of the working NW, it means working filter, +1 if the N was less than 1, 5 number of the working +2 if it was between 5 to 30, and only the working +4 when it was more than 30, and when I say the Q or this N is equal to 0.25 Q square root of the Q. While for the slow sand filter, usually the working and the cleaning, they should usually be more than 2, all of it. And the others, these are not you wanted them in the design process, but these are all important numbers. We should have take care about the. This is a cross-sectional area of the filter. Let
Doctor?
me, yes, yes, please. Hello?
Is that table given in the exam?
Yeah, these
Doctor?
are all.
Is that?
Can you hear me?
Yes, sir.
Yeah, the table will be, this table will be given to you mostly, to you, but you have to take care about this part, and this may not be included for you. You have to know how to use this one, but the other numbers, it will be given to you. When we have a treatment plant like this, it will we have 48,000 meter cube per day. This is a flow that's needed, and usually when for this city, usually the maximum water flow will be used. This is the capacity of the treatment plant. Now, water treatment plant is designed to treat the 48,000 meter cube per day. 12 rapid sand filters have been used. Means we have the Q and we have 12. And by the way, this is filters. So we have the Q, which is equal to 48,000. It will be like this, divided in two parts. So 12 rapid sand filters, and we have the Q is 48,000 meter cube per day. Now, what will be the Q per one filter? Okay, each part, this is filter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So how much it will be the Q per one filter? Hello? Mister? Have fun. Anyway, the Q per one filter will be equal to the total Q that we have divided by the number of the filters. So we have the Q, which is 48,000 meter cube per day, divided by 12. And this is gonna give you per day. Okay, so so it will give you 4. So the Q per one filter is equal to 4,000 meter cube per day. This is first, without anything. The filtration rate, the FR, is 116 meter per day. Okay, so the filtration rate is equal to 116 meter per day. And the backwash rate, filter backwash rate, is equal to 864 meter per day. And we say, what is the difference between this and that? This is the Q divided by area of the filter, which QQ are normal. This is the Q backwashing divided by area of each filter. Now, what is the required? The required is to design this filter based on the design of this filter. So actually, we have for one filter we need only 4,000 meter cube per day, and we have the filtration rate is 160 meter per day, which is equal to Q over area. Now we have the Q is 4,000 meter cube per day, and the area. Now from this one, I can say area of the one filter is equal to 4,000 divided by 160 meter cube per day per meter per day, which gives you 400 divided by 16. It's equal to 25. So 25 meters square is needed just for that filtration rate. Now, what it said, I want to see what is the length to the width of each filter. I should assume one of this one. What will be this 25 will be like this. The area is 25. We have the length and the width. It has been given to you that we need 2 troughs to be used in this filter. We say the troughs are used for getting all the filtered materials, and it will put it in this way, in the longitudinal direction of the way. So 2 filters, here's 2 filters. Now I just want to tell you that the filter, the trough, this is the trough. The trough are channels used just for collecting the backwashed filter, and they should have at least a space between each of them, 1 meter to here to 1 meter. So the center line of this trough is worked for 1 meter. So 1 to here and 1 to here. Now when we have 2 troughs, it means that the width of this tank, it will be for 2 meters. If I have 3 troughs, then the filters will be 3, like this. Let me show it to you. Yeah, if I have, this is 1 trough. This is the top view. means that if you want to check this one, there will be only one trough here. And this will be fixed from this wall and by this wall. So the water is going after the filtration. This will be back washing. Just go inside this tank. And so the distance here is 1 meter from the wall to the center. If I have two troughs, so here's one, and there will be 2 meters between them. So the width will be 4 meters. Look at this one. 1 meter from the wall, and there will be another 1 meter. That means we have only 2 meter for the trough and another 2 meter for the second one. So the total width is 4 meter. And based on that width, you can find the length. We say that in our exam that we have 25 meters square, which is equal to L times W. W because of two troughs. So it will be equal to 4. So L equal to 25 divided by 4, which is equal to 6.25. So this is will become the length and the width of the filter. Do you have any question right now? No question? I hope so. I hope you understood all the materials that I explained to you.
No, doctor, thank you.
Okay, thank you. Part 2 and part 3 we will solve it in the next lecture. Okay. Part 2 actually it asks us about the dimension of that trough. We said we have two troughs. So the y is the b is the base of the trough, and the y is the depth of the trough. Now, how much it should be? We have one equation that will govern the y and b, which is here. Yeah, this is going to be used to design the troughs. The troughs, if we have the base and the depth of the trough, so we have to, when we have y is this one, we have to have the q. This is the q backwash. We have the filter backwash rate is equal to Q of the backwashing divided by area of the one filter. In our case, the area of one filter is 25, and the Q of the backwashing it should be used. I don't have it, I have to find it, but I have this one, which is the 800. Yeah. 864 meter per day. So this 800 meter is equal to Q backwashing divided by area of one filter. Area of one filter is 25 meters square. So from this one, I can get meter per day, and we have 25. So the Q backwashing is equal to 25 times 864 meter per day. And this is the whole backwashing, which is equal to 25 times 864.
21,600.
Okay, 21,600 meter cube per day. This is for both backwashing. It means this is the flow that's needed just to backwash the filter. Now, how much of this water will come in each trough? Because we have for each by the way, this is should be divided by 2 because we have two troughs. As we have, it's given to you, we have to use two troughs. It means this is the cross-sectional area of that. So the filtration rate, the Q backwashing, it's equal to, as you said, how much? 21,600. So 21,600 meter cube per day for this area. So each trough will hold at least half of this one. So Q per trough is equal to 21,600 divided by 2. Now, why I need to know that? Because in this equation, this is the Q backwash discharge reaching one trough. the one trough, and it should be in meter cube per second. So 21,600 meter cube per day divided by 2 is equal to 10,800, right? Meter cube per day. And I wanted to convert it to be per second. So divided by 24, divided by 3660, it will become 0.125 meter cube per second. Why I need to know that? Because I want to see how much is the y. The y is equal to 1.73 times third root of 0.125 divided by g, which is the 9.81 divided by b squared. Now you have one equation with yb. Usually we will assume y equal to b or use square one. So square one, it means that this is by and this is b. I will assume this is b, and from this one I can find the b. The b is to be this is b cubing that b, and then dividing, find the b. This is will help you to find the dimensions of the trough. Yeah, that like this one. So you have to convert it to per meters per second. This is the cube per one trough. And when I assume this is qy equal to b, I am assuming the trough is square. That's one. So applying this one, you can get b equal to y. So I will use a trough of 0.40 centimeter. It is 0.40 meter, sorry, not centimeter, 0.4 meter. Then the 0.4 by 0.4 trough will be enough to hold the cube back washing to this trough. Now, how much is the water can be collected during 5-minute back washing? It's easy. I have the filter back washing rate times this is meter per day times the time. This is the time for washing. This filter will be backwash for 5 minutes. It will work for 24 hours, and you have to wait then 5 minutes backwashing until restart this one. So 5 minutes, and then it will be meter per day. I will just convert meter per day to minutes. It will be 24 hours, 16 minutes. So this minute will be cancelled out day. And then the area of the one filter is 25. And then I have to double that amount, because this is 2 for washing 2 filters. We have 12 filters. I want to wash 2 filters each time. So this is 150 meter cube is the volume of water that is needed just to be used for washing the 2 filters out of 12 filters for 24 hours. I think, yeah, this was the required. This is the 5 minutes given to you, and the 2 filters that will be washed together in the same time. I wanted water disinfection. It will be for the next lecture. I want you just to review this lecture and watch this video carefully, and I will assign for you another assignment related to filtration.
Doctor?
Yes.
Starting from the next class, can you move a little slower? Because sometimes we cannot get part of the question and we will move to something else. So that will mess up. We will